So continuing the proof, so this is to show that 5 implies 1. So given epsilon greater than 0, the condition in 5 was that it is almost measurable. So there exists a measurable set let me write it as U epsilon such that the outer measure of U epsilon symmetric difference with E is less than or equal to epsilon. So what we can do is for each n greater than or equal to 1, choose a measurable set. So measurable here always means measurable means lebesgue measurable, because we are only dealing with lebesgue measurable sets for now. Later on we will come to other measurable measures and other kind of measurable sets, but here by a measurable set we mean a lebesgue measurable set. So for each n greater than or equal to 1, we choose a measurable set un such that the outer measure of un symmetric difference with E is less than or equal to 1 over 2 to the power n. So we are choosing for each n epsilon to be 1 by 2 to the power n, and we can choose for that epsilon a measurable set which we denote by un such that the symmetric difference has outer measure less than or equal to 1 by 2 to the power n. So this implies that the outer measure of un minus E is less than or equal to 1 over 2 to the power n, and the outer measure of E minus un is less than or equal to 1 over 2 to the power n. So now we take the union of all these u's which we denote by u prime. So take the union n equal to 1 to infinity of these u's, and I claim that the outer measure of u prime minus E is equal to the outer measure of E minus u prime, and both are equal to 0. So let's try to show this. So to show that the outer measure of, let's say, u prime minus E is equal to 0. Now u prime minus E, this is equal to m star of, so u prime was the lim sup, so we had the intersection n equal to 1 to infinity of the union m equal to n to infinity um minus E, and this is equal to m star of the intersection of all the sets union m equal to 1 to infinity um minus E. And now note that the intersection, since the intersection of all these um minus E is a subset of, so m equal to n here, is a subset of m equal to n to infinity minus E for any natural number n, because we are taking the intersection here of all n. So if you fix any n, capital N, then this intersection is a subset of the part of the lim sup that starts at m equal to capital N. So this implies that m star of the intersection u m equal to n to infinity u m minus e is less than or equal to the m star of m equal to n to infinity u m minus e for any n belonging to n. And now the right hand side is less than or equal to the sum m equal to n to infinity m star u m minus e, and each of them is less than or equal to 1 over 2 to the power m. So this whole sum is less than or equal to the sum from n to infinity 1 over 2 to the power m, which is equal to 1 by 2 to the power n minus 1. So this is true for, since this is true for any n, this inequality which says that m star of u prime minus e is less than or equal to 1 over 2 to the power n minus 1 holds for any n. This implies that m star of u prime minus e is equal to 0, because you can have n as large as possible, since n can be taken as large as possible. So m star of u prime minus e can be as small as possible, and so in fact it is 0. Similarly, to show that m star of e minus u prime is also 0, so this is to show again. So now we have m star of e minus u prime, this is equal to m star of e minus, I'll just write down the definition of lim sup again, m equal to n to infinity u m, and this is equal to m star of e intersection with the complement of the lim sup. So now we can rewrite this m star e intersection. So the complement n equal to 1 to infinity union m equal to n to infinity u m whole complement, this is equal to m star e intersection union. So I am going to use De Morgan's law. So union n equal to 1 to infinity, because the intersection changes to union because we have a complement, and inside we have union m equal to n to infinity u m complement. So this can again be rewritten as e intersection union n equal to 1 to infinity, and now I am again going to use De Morgan's laws. So you get m equal to n to infinity u m complement. So now we can take this e inside the union of these sets. So you get m star union n equal to 1 to infinity e intersection m equal to n to infinity e intersection u m complement. So this is nothing but this set, this whole set is nothing but the lim inf as n goes to infinity of these sets e minus um, and because the lim inf is contained in lim sup, we have an inequality lim sup E minus un, so there is an n here, E minus un, and again we can use a similar argument as above to show that this is again bounded above by 2 to the power n minus 1 for any n belongs to n. So in the end we have on the left hand side E minus u prime, which is bounded above by 1 over 2 to the power n minus 1 for any n belonging to the natural numbers, so as large as possible. So this implies that E minus u prime is equal to 0. So we have shown that both E minus u prime and u prime minus E have so we have proved this claim that both u prime minus E and E minus u prime have outer measure 0. Now how to use this fact to produce an open set? Now we have to produce, our goal is to produce an open set, so this is what you want to prove the first item, because we are starting from 5 and then we are trying to prove 1. So this is the first item, is to produce an open set V containing E such that the outer measure of V minus E is less than or equal to epsilon. So to do this, note first that both u prime minus E and E minus u prime are measurable, since both have Lebesgue outer measure 0, outer measure 0. So we have already seen that such sets are Lebesgue measurable. So this implies that u prime union E, which is now which can be written as u prime union E minus u prime, this is a measurable set. This is a measurable set because since u prime is Lebesgue measurable, remember that u prime was the intersection of the union of the UNs. So each of these UNs are measurable, which means that this countable union for each n is measurable, which means that this intersection is also measurable. So from our class of Lebesgue measurable sets, we see that u prime is Lebesgue measurable and E minus u prime is also Lebesgue measurable. So both are Lebesgue measurable sets. So the union u prime union E is Lebesgue measurable set. So given epsilon greater than 0, there exists an open set V containing u prime union E such that m star of V minus u prime union E is less than or equal to epsilon. Now because V is a superset of u prime union E, this also implies that E is a subset of V. So I claim that this is our required open set and m star of V minus E is less than or equal to epsilon. So let's draw a Venn diagram of what's happening here. So you have E and you have another set U, and you have the set V containing the union of U and E. So I claim that V minus E is contained inside U prime, so this is U prime minus E union V minus U prime union E. So let's see what is U prime minus E. So this is this part, this is U prime minus E, and V minus U prime union E, this is given by this part which lies outside U prime as well as outside E. So all this part in the green shaded region is, this is V minus U prime union E. So in fact it's not very difficult to show that V minus E, which is kind of the union of the red and green parts, is a subset of the union of the red and green parts. So one can just see it visually, but again as an exercise, check this using set arithmetic. So now we are done, because m star of V minus E is less than or equal to m star of U prime minus E plus m star of V minus U prime union E. This is 0 and this is less than or equal to epsilon, so this is less than or equal to epsilon. So we have found an open set that contains E and m star of V minus E is less than or equal to epsilon. So this proves that 5 implies 1.